This is a part 2 for the chapter 4 for the heat exchanger, that we are going to look for the log mean temperature difference method. So next we're going to look on the log mean temperature difference method, which is you're going to use this to do the analysis for the heat exchanger in order to determine the sizing or the capacity of the heat exchanger. So throughout the end of this chapter, which is the design consideration, there will be the evaluation, the differentiation between the usefulness of the log mean temperature LMTD method and the effectiveness NTU method. Okay, so you are going to use whether LMTD or effectiveness NTU method. So there are, two ways of you're going to look of this one. Either you're going to choose with the LMTD method or effectiveness NTU. Okay, so analysis of the heat exchanger. If you look on the first law of thermodynamics, where the heat transfer to the cold fluid must be equal to the heat transfer from the hot fluid. So which means that if you look on the hot fluid, it will give you the heat transfer to the cold fluid. So whatever the heat released from the hot fluid will be absorbed by the cold fluid. So that is our first assumption, where the heat exchanger will follow the first law of thermodynamics, where the numbers of the total rate of heat heat will be rejected from the surrounding and then will be absorbed by the another systems in order to do the energy balance. Okay, so this is for the counter flow. Okay, where the cold fluid enter in this position and then the hot fluid enter this position. So the temperature difference between TH in and TC out, and this is TH out and TC in, which give you the temperature difference delta T for the inlet condition delta T1 and outlet condition delta T2. You have to remember that it has to be constant. So in heat exchanger analysis, it is convenient to combine the product of the mass flow and the specific heat of the fluid. So where we call it as a heat capacity, this one. So the heat capacity is the mass flow rate times with the specific heat at a constant pressure for the fluid. Okay, so this is for the hot fluid and this is cold fluid. For the cold fluid, we know as the CC, and hot fluid as the CH. So thus, the rate of the heat transfer for the hot fluid, for the cold fluid, given CC times with the temperature difference TC out minus TC in, and then rate of the heat transfer for the hot fluid, which is hot fluid, the heat is rejected from the system to the surrounding, and this is why it is a positive, because the heat is absorbed from the system to from the surrounding to the system. That's why it gives you positive signature, and negative signature because heat is rejected from the system to the surrounding for the cold fluid. So if we differentiate between the cold flow and the counter flow from the parallel flow and the counter flow, the delta T naught is the difference between TH in and TC in, and that's why this one, and this is delta T and delta TL. Okay, so delta TL for the different changes for the outlet, and delta TO different changes for the inlet, and this is given by the schematic for the concentric tube. Okay, as for the parallel flow and for the counter flow. So the heat flow between the hot fluid dq is given by this equation, where U is overall heat transfer coefficient, A is the surface area, and delta T is the temperature difference. The heat gained by the cold fluid is given by dq cc dt, and the heat given out by the cold fluid is minus ch dth. So by considering this, however, since the temperature difference between delta T of the hot and cold fluid varies with the distance along the heat exchanger, it is convenient to use the mean temperature difference between the hot fluid and cold fluid. So thus Q will be equal to the A U overall heat transfer coefficient times with the delta Tm, where delta Tm is the mean temperature difference. So the question now is how to calculate the mean temperature difference. So the next derivation is to define the log mean temperature difference equations. Okay, so if you consider this, where the delta T dTH for the hot fluid and dTc for the cold fluid, let's consider for the parallel double pipe heat exchanger. Okay, so delta T1 is TH in, delta T2 is the TH out. Okay, so dq is UTH minus TC times with the DAS. With this, dTH is equal to, reorganize back the equation, previous equation, which is equal to minus dq over CH, and then dTc is dq over CC. What we have here is the difference. We give dTH minus dTc, which is equal to minus dq 1 over CH plus 1 over CC, which if we put this into this equation, okay, and then substitute in the previous equation, what we have is the integrating from the inlet for the heat exchanger, plus minus sign given for the parallel flow or counter flow. Okay, so that we have solving this equation, where finally we skip part this one. Yeah, so the rate of heat transfer is equal to UA delta T2 minus delta T1 over natural log delta T2 over delta T1. So this is actually the log mean temperature difference, delta Tm. So delta Tm is equal to delta T2 minus delta T1. So delta T2 is the temperature difference at the exit. Delta T1 is the temperature difference at the inlet. Okay, so this is the delta T1 and this is the delta T2. So delta T1 for the parallel flow is the temperature change between the hot fluid and cold fluid, where delta T2 is temperature change between the hot flow and cold flow at the outlet. Whereas for the counter flow, delta T1 is given by temperature change between hot flow in and cold flow out. Okay, this one. And delta T2 is temperature change between hot flow out and cold flow in. So this LMTD method is only strictly limited to single pass, parallel and counter flow. However, it also can be used for multi-pass shell and tube exchanger with the application of the correction factor. So delta Tm is equal to correction factor times with the delta T LMTD for the counter flow. For the shell and tube cross flow heat exchanger, the log mean temperature difference will be considered for counter flow heat exchanger. Okay. So the correction factor may be used with the several common configuration which is available in the standard chart, which is available in your textbook, where given by P and R. So what is P? By this temperature difference, which is P and T, P and R is given by this signature. Okay, so the capital T is referring to this one, and this is for the small t. Okay, all right. Similar for this is for the single shell, one shell pass, and then can be applied for 2, 4, and 6 multi tube. And this is the 2 shell. This is for the cross flow unmixed, and this is cross flow. Sorry, this is cross flow unmixed, with both unmixed, and this is cross flow with mix. Yeah. So one example that you can go through, okay, which is this is a single concentric tube by applying the log mean temperature difference method. Okay. All right, so you can go through this from the PowerPoint slide that I give you. Yeah, so by the end of this subsection, you have to submit an assignment. So when is the due date? The due date will be on the 15th of May 2020 by 5 p.m. I will update this in the assignment in the Google Classroom. Okay, and then this is for LMTD correction guided tutorial. Then you also need to submit this by 15th of May 2020. Okay. All right. So this LMTD method, the requirement that you need to know in order to analyze the rate of the heat exchanger is, firstly, you need to know the temperature difference and the mass flow rate. But if you don't have the temperature difference, you cannot have these things. So which means that the requirement from the Q, which is UA delta Tm. Okay, so you need to have to calculate the delta Tm, you need to know the delta T1 and delta T2. So this delta T1 and delta T2 is the specified temperature that you need to know before you can do this analysis. Okay, and then U and A. So U and A is overall heat transfer coefficients. So the designer, either you need to predict the delta Tm, or you need to know the sizing of the heat exchanger prior to do this analysis. So this is the likeness when you want to do the analysis by using the log mean temperature difference, because the specification that you need to know is the temperature itself. So before that, the value for UA is also required. Thus, if you are designing a new heat exchanger, you cannot use the log mean temperature difference method. So the log mean temperature method is only suitable to analyze the effectiveness of the heat exchanger, but not to analyze the design itself. Okay, so the best suit to do the design process for the heat exchanger is by using the effectiveness NTU method. Okay, but actually in actual condition, the combination of the NTU and LMTD method is required to obtain the best design for the heat exchanger. Okay, so the LMTD method, in summary, you need to, this is the equation, QUA delta Tm, and then the delta Tm is given by these equations. Then this is how to find the delta T1 and delta T2. Okay, so this figure is very important, and this schematic. Okay, all right, so this is a correction